Hello. Hi guys. Good afternoon everyone. Good afternoon. So we'll start today's session exactly by 2 o'clock. Okay. So let everyone join. So today we are going to discuss a very important topic on a plastic analysis of steel structures. Good afternoon. So I hope you all had lunch, right? Hope you're a bit sleepy today. See, after lunch, so definitely there will be, a bit drowsy, but still because of internet, connection problem, so I just postponed my class to, afternoon session. Yeah, guys, come on, come fast. Guys, come on, I'm already in live. Yeah. We'll start exactly by 2 o'clock. Okay. So we are going to discuss today's topic on plastic analysis and design of steel structures. Manideep, yeah, good afternoon. So what about the rest of guys? Come fast, guys. I request all of you, so please join soon. So by that we can start this today's session.
भगवान शिव आदि Mandeep, yeah, good afternoon. So what about the rest of guys? Come fast, guys.
Joseph Kishore, yeah, Vamshi Rathod, yeah, good afternoon. Very important topic. So which is playing, topic which is very important in all competitive exams, GATE, AE, AEE, even in IAS examinations. So definitely 2 marks will be there from this plastic analysis. See, if you understand this plastic analysis, so by that you can able to do the beam designs. Okay, so based on this analysis itself. So limit state method is completely working on this plastic analysis only. Okay, Trilok ready? Yeah, good afternoon. So actually this presentation was scheduled 2 o'clock, so let me wait for 4 minutes. Okay, so let everyone come, by that I can start immediately. Yeah. Bharadwaj, yeah. So Bharadwaja is also viewing. Rakesh Reddy viewing. Yeah. Hi, good afternoon, Rakesh. Muhammad Al Yusufi. Yeah, good afternoon. So we will start in 2 minutes. Okay. So let everyone come. Good afternoon, Rakesh. Okay. Yeah, good afternoon, Anusha Reddy. Good afternoon. Srinivas, good afternoon. Tirupati Manideep, good afternoon. Yeah. See, very important topic, Amma. So let me wait for everyone. So who is the other? Yeah. Is my voice is audible to everyone, guys? So please respond. Is my voice is audible to you? Is it clear? Can anyone? Is my voice is audible? Guys, please respond. Anyone out of 10 viewers, please respond. Is my voice is clear? Yes. Okay. Trilok, good. Thank you. Thank you, Trilok. Okay. So let me start the presentation. Yeah. So good afternoon, everyone. So today we are going to discuss on plastic analysis. So which is one of the important concept in design of all structures. Okay. So nowadays people started using this plastic analysis only in terms of limit state design. Okay. So this analysis is going to help you out in terms of designing civil engineering structures. Okay. So which is under a limit state design. Okay. Yeah. So let me first show you the idealized stress strain curve of a mild steel, right? So because our topic is completely relates on the stress strain behavior of a material, right? So which is a steel. So I think you all know well about the stress strain curve of a mild steel, which is an idealized stress strain curve. So here you can see, yeah. So here you can see the limit of proportionality, so where your member is linear, so where the stress is directly proportional to strain till this point, right? So from here member reduced in its strength and increases in its strain. Okay, so this is called the portion where it is completely elongation without any increase in stress, and then the strain hardening takes place. So let me show you one more in the same way. Yeah, so here also you can see the same. So this zone is called an elastic zone, right? And this is a yielding zone, and the strain hardening zone, and the next one is necking zone, right? So till this point your member is behaving elastically, right? So where your stress is directly proportional to strain. So from here it is completely under plastic. Okay, so this is completely under plastic zone. So where which is under, this is under elastic zone, isn't it? So from here, so where you are supposed to treat your member by considering its ultimate stress. So within this elastic zone your member will have a proportionality limit and elastic limit. See, whatever the analysis you do for a material, so if you consider its yielding only, so then the analysis comes under the elastic analysis. Okay, so from this point to this point, if you try to take your member and start analyzing, So you have to consider member under its ultimate stress, okay, because that is a maximum stress where the member is subjected to, okay, show its strength when it is subjected to failure. So here the yield point or yield stress is the highest design stress for steel, so where under yield point. And coming to the plastic zone, the highest stress point is an ultimate point, okay. So I think we all know about the stress strain curve of an steel. And here you can see the idealized stress strain curve, which is considering in our plastic theory. So this is called a linear, isn't it? So where the stress is directly proportional to strain. So this is a non-linear, so where your stress is not at all proportional to its strain. So this we are considering it as a plastic analysis, plastic theory, okay. Yeah, so you can see the same even in this picture also, in this graph, right? So this, whatever the Young's modulus you calculate within the non-linear curve of the stress strain, so here you can get the hardening modulus, so which it is not at all an elastic modulus. So the elastic modulus in the sense where your stress and strain should be directly proportional. For our engineering materials, we all have, materials will have an Young's modulus within its elastic zone only. So whatever the modulus you calculate in non-linear curve, so that modulus comes under the hardening modulus, which varies at every point, okay, and again it won't be same. So why? Because at that particular stage your member is non-linear, and where it shows a different modulus values at every point, okay. So, and other important parameter where we should know the difference between the factor of safety and partial safety factor. So here factor of safety we define as yield load to its working load, isn't it? So which talks about the working stress design, isn't it? So coming to your partial safety factor, how you define a partial safety factor? Partial safety factor is nothing but ultimate load to the design load. So in elastic analysis we consider, in elastic analysis we consider factor of safety. In plastic analysis we consider load factor, okay. So load factor, how we get the load factor? So which is an ultimate load to its design load, okay. So where we get the load factor, which is nothing but a partial safety factor of the materials. So the main difference between elastic analysis and plastic analysis was clearly described here. So in elastic analysis we treat material which is in elastic state, but in plastic analysis material is in a plastic state. In elastic analysis the performance of structures will be under only service loads. So service loads in the sense working loads or permissible loads, okay, so which are under working conditions. So now all our structures are under service, all the structures are under working condition. So coming to plastic analysis, performance of structures under ultimate or collapse load. So this won't be seen in any structure until it is subjected to its maximum load, okay. So now all structures are under service, but we design the member to take care, to carry it to its ultimate or its collapse load. So that is the difference between elastic analysis and plastic analysis. The other difference, deformation increases with increasing load, isn't it? In elastic analysis your deformation will always increase based on the increasing load, but in plastic analysis deformation or any curvature of the member without an increase in load also. That is what we have seen, the strain hardening zone. Without increase in stress there is a deformation in the member, so that is called as a strain hardening zone. Without increase in stress there will be only increase in strain. Got it? So that is how the plastic analysis is also, okay, defined as. Got it? Yeah. So next let me give a brief definition of a plastic analysis, so which was given by Professor S.R. Satish Kumar and Professor A.R. Santa Kumar. So they are giving NPTEL lectures on design of steel structures, which is one of the outmost NPTEL lectures given by them. See, in plastic analysis what is defining? a design of a structure, here the important is ultimate load of the structure as a whole is regarded as the design criteria. So in plastic analysis, we are considering ultimate load as its a design criteria. Okay. Then the term plastic has occurred due to the fact that ultimate load is found. So what we found, the ultimate load is found from the strength of steel in the plastic range. So here the ultimate load, whatever we found, it is from the strength of steel. Okay. So within the plastic range only we consider its ultimate load. And then this method is rapid and provides a rational approach for the analysis of the structure. So nowadays, for analyzing the structures, we are using the plastic analysis to analyze the structure and we start designing. So it also provides a striking economy as regards. Why? Because when you are considering the member capacity to its ultimate load, definitely you can make use of the section and you can decrease the section based on the load applied. Okay. The weight of the steel, since the sections required by this method are smaller in the size. This is how the plastic analysis is more economical than the elastic analysis. Why? Because elastic analysis is completely considering its working loads, where working loads create members to increase in its sizes. But in plastic analysis, it considers its maximum strength or a collapse load, which can reduce the sizes. So where we can make use smaller in sizes than other required by the method of elastic analysis. So this is also one of the important point we need to understand in the plastic analysis. See, and one more point, plastic analysis and design has its main application in the analysis and design of statically indeterminate framed structure. So we are using this plastic analysis mainly in all statically indeterminate structure. So as we know, when the unknown forces are more than 3, definitely the structure is going to be an indeterminate structure. Okay, all our portal frames, like all fixed supports, fixed beams, like proper cantilever beams, continuous beams, even all framed structures comes under the indeterminate structures. See, for analyzing those indeterminate structures, plastic analysis is one of the important tool where we can make use of. Okay. Yeah. So here, before explaining about this, let me one second. Yeah. So let me show you a small video. So here the difference between the mechanical hinge and plastic hinge. Can you tell me what do you mean a mechanical hinge? The hinge which we are providing, okay, based on the mechanism, right? So let me show you. So this is a beam which is supporting on 2 supports. One end is a pivot support and the other one is a roller support. So here the support reactions are 2. One is horizontal support reaction, the other one is vertical support reaction, isn't it? So here what is not present? Moment is not present in that particular joint, isn't it? At that particular support, moment is not provided. So mechanically we are not providing a moment where it can easily rotate on its own. Okay, so that is how we are using the pivot support, which is a mechanical hinge we are providing. So in reality, this is provided by us, which resists 0 moment at that particular point. But coming to the plastic hinge is not a reality. Plastic hinge is a concept which we are considering for designing the structure. Understood? So that is a major difference between the mechanical hinge and the plastic hinge. So mechanical hinges are the one which we are providing, okay, to analyzing the structure, but plastic hinges is a concept. Here coming to the moment, resists a constant moment which is a plastic moment. Understood? So in mechanical hinge there is no moment, but in plastic hinge there will be a moment. So that moment is a plastic moment which is going to be a constant moment. Okay, so the mechanical hinge is equal to plastic hinge with where the plastic moment is equal to 0. Okay, so that is what the concept of making use of mechanical hinge for our general structural analysis, which is a elastic analysis. But in plastic analysis, the hinge concept we are going to consider to analyze the member at its ultimate load and calculate the maximum moment at its plastic zone. Okay, so that by that this moment is going to be a plastic moment. Okay, So let me show you some pictures where we can able to understand how the plastic hinges forms in the real structures. Okay, so here you can see the loss of concrete cover. So this is a framed structure which was constructed for the testing itself. Okay, it is not under usage, it is only for testing purpose. See, you can see a framed structure. So beam, column and slabs. So here you can see in column there is a loss of concrete cover, and here in the column you can see the curvature of the column. So why? Because the column is not straight. So you can see some kind of crookedness in the columns. And this picture shows the displacements during test. So when it is under test, when it is subjected to a lateral pull, so you can find the sway in the structural elements, isn't it? So here try to observe carefully. Collapse by failure of the bottom of the columns. So here the bottom of the column was collapsed here, and formation of hinges on the beams. At beams you can see the hinges which was formed when it is subjected to a maximum load more than its carrying capacity. See, when a member is subjected to maximum load more than its carrying capacity, definitely there will be a possibility of hinges in that member which makes member to rotate. Okay, so that is how the plastic hinges formed in these beams. So then what happens when plastic hinges forms? Your structure will collapse like this. So here you can see the first hinges which was formed in the column at the bottom supports of the column and the support at the beam. Chusara? So at the beam column joint, hinges are formed here. Okay, in the bottom story, in the ground floor, I can say. And more pull, the hinges were formed even in the second story, right? And this is the final collapse mechanism, how the structure was failed due to hinges formed at every joint. I can say at every support. See, you can see ropes which are pulling the structure. So this force is making your building collapse. Okay, so by that you can find the hinges which are formed, plastic hinges which are formed at every joint. See, this is one hinge, and this is the other hinge, and this is the hinge. So 4 hinges are formed at the column beam joint, and here also you can see hinges which are formed, and even the bottom of the column to the foundation also you can see where the hinges are formed. So this is how when member is subjected to a maximum load more than its carrying capacity, hinges will definitely form. I will show you where the hinges will form in the structure. Okay, when it is subjected to load. Okay, I will show you in clear pictures also. So you can see how it happened. So let me play again. Guys, so please try to observe carefully. So can you tell me where the possibilities of hinges? So there is a possibility of hinge here, here, and this is the location, and this is the point, and even at the supports also. Okay, so this is the points where the hinges forms, and member first fails at the hinge point because it is not resisting towards its moment. So where member will fail at the particular hinge point. Okay. Yeah. So let me continue and see the method of plastic analysis. So here we are going to use plastic analysis in few methods. One is static method and the other one is kinematic method. Okay. So what do you mean static method? Static method in the sense where your structure, the forces are stable. Okay. Without any deformation. So without any movement in the force. So lower bound, a load computed on the basis of an assumed equilibrium. Bend moment diagrams in which moments are not greater than the plastic moments is always less than the true ultimate load. So that is what the equilibrium method exactly means. And coming to your kinetic method or mechanism method, which can also be called as a virtual work method. See, static method or equilibrium method is gonna used for determinate structures. Kinematic method or mechanism method or virtual work method we use for the indeterminate structures. Okay. So we can make use of these two methods in plastic analysis. So coming to your indeterminate structure analyzing with the help of plastic analysis, work performed by the external loads is equated to the internal work absorbed by plastic hinges. Understood? So the work performed by the external loads is equated to the internal work absorbed by the plastic hinges. That is what exactly we do in the kinematic method. So here we are considering it as a lower bound of the structure. Here we are considering it as an upper bound of the structure. Upper means greater values. A load computed on the basis of an assumed mechanism is always greater than or equal to true ultimate load. So we always consider the maximum carrying capacity of the structure. Okay. So where in the kinematic methods. So here we consider is always less than the ultimate loads. So less than the ultimate load means it may be not under failure, but it may have the permanent deformation. Okay, both will be under plastic analysis. See, if you see the stress strength of your mild steel or member from its yield point to the ultimate points, completely that zone is a plastic zone, isn't it? So greater than the ultimate point, you may not see the complete failure, but you can see the permanent, permanent deformation where the member is supposed to get a failure. Okay, but in less than its ultimate load, there will be only the permanent deformation, but you can't see any crack in the structure. So that is how the plastic analysis can make use of static method and kinematic method in its analyzing. Okay, and see here the materials. So elastic, the other one is elastic perfectly plastic material. So that's what I am letting you know about this. This is the elastic limit where your member is linear, and this is elastic limit, and this is the plastic zone where your member is elastic perfectly plastic. So where when it is unloaded, so this is how the permanent deformation takes place in the member. Okay, what are the assumptions to have when you are doing this plastic analysis? See, I think when you do elastic analysis also you have few assumptions, isn't it? What are the assumptions? Member obeys Hooke's law, member is homogeneous and isotropic, isn't it? So like that, even members never changing in its plane even after bending. So these are the assumptions what we made in elastic analysis. The same kind of assumptions which we are making in plastic analysis. Plane sections remain plane even in plastic condition. Stress strain relation is identical both in compression and tension. Okay, there won't be any change in stress strain relationship both in the compression and tension of the member. Okay, so that these are the assumptions what we made in the plastic analysis. And the process of yielding of a section. So as we know, this is the pure bending equation where moment of resistance is equal to the bending stress into section modulus of the member, right? So this the equation which we derived based on the pure bending equation, which is considering member under elastic limit, isn't it? So elastic limit, which is yield stress reach my is equal to sigma into y into z. So here when the member is reaching its yield point, by that your moment of resistance is equal to the bending stress into section modulus. So I think we all know this equation based on the pure bending equation, right? So let me show the bending stress diagram of a beam when it is subjected to a lateral force. See, this animation shows an internal forces developed in a beam when it is subjected to lateral force in its longitudinal length. Okay, let us take a beam which is subjected to lateral force. By that I can able to understand at supports your shear force will be more, towards center your shear force will be reduced. Towards support your moment will be reduced, towards center your moment will be more. Okay, so that the picture what it is showing now. See, at center your shear force is almost zero, and where you are having the maximum moment. So by that, whatever the bending stress you calculate, you should calculate at center of the beam when it is subjected to a simply supported, okay, member. So towards support what happens? See, towards support your shear force is increasing and your moment is reducing, right? So let me show you again. Right? Yeah. So first you have to understand this. Then coming to our concept. So this is the bending stress diagram of a rectangular beam where the bending stress is 0 at its neutral axis. Bending stress is maximum at its outmost layers of the member, isn't it? So here from this diagram I can say your member is obeying Hooke's law, where your stress is directly proportional to strain. Why? Because you can see the complete linear graph. So where your moment is less than the moment yielding, right? Okay. Next, coming to the second one, when the moment is equal to the moment yielding, at that point also your graph will be linear. Then now member is behaving plastically, member is going into permanent deformation. You can start the non-linear curve started at its outmost layers like this. When your yield moment is less than moment applied, which is less than plastic moment, right? And then finally complete your graph, your bending stress diagram is gonna be non-linear, so where your moment is equal to a plastic moment. So this is the varying of the member when it is subjected to load. So these zones are happen when it is under elastic zone. This happens when it is under plastic zone. So whatever the pure bending equation we derived, that pure bending equation m by I is equal to sigma by y is equal to E by R, that was derived based on the elastic analysis. Okay. So but we are going to derive our moment under plastic analysis by considering its ultimate load. Now I will show you how to calculate the plastic moment based on its plastic theory. Okay. So this is the same example where I showed inverted T-beam. So here the plastic hinge concept. Why the plastic hinge concept came into picture? See, when the section is completely yielded, the section is fully plastic, isn't it? See, after the yield point, what happens? Member goes into its plastic zone. ఎప్పుడైతే సెక్షన్ కంప్లీట్ గా yield అయ్యింది అని అన్నాము అంటే what it means? Section is fully plastic అని అర్థం. A fully plastic section behaves like a hinge. So when a member is having a permanent deformation, that plastic section behaves like a hinge. After its plastic zone only, member will tends to fail. So when it is failing means it is losing its what? Losing its property. ఏం ప్రాపర్టీ లూజ్ అవుతుంది? అది మూమెంట్ రెసిస్ట్ చేసే ప్రాపర్టీని అక్కడ లూజ్ అవుతుంది అనమాట. See, let's take an example of a fixed beam. So when you try to elongate, your member is having a resistance in all directions in terms of moment, in terms of horizontal elongation, in terms of the vertical displacement, isn't it? See, when it is having a failure, what happens? It shows it's a plastic hinge at that point where it is tends to rotate. So that is how in plastic section it behaves like a hinge. That is how the plastic hinges forms in the member only in its plastic zone. So plastic hinge is defined as a yielding zone which is due to bending in a structural member, at which large rotations can occur at a section at constant plastic moment. Okay, so that is how the plastic hinge concept came into picture in the plastic analysis. Okay, so let me define about the shape factor. So what do you mean shape factor? So here the ratio of the plastic moment to the yield moment. I can call it as yield moment, can also be called as an elastic moment and kuda anachu. Okay, the ratio of plastic moment to the yield moment is known as the shape factor. So MP by My is known as the shape factor. Can you tell me what is MP now? MP is equal to shape factor into My. So that means whatever the moment of resistance we calculated based on the pure bending equation under elastic limit, it will be for example, we got some shape factor of some value of 2. Okay, so can you tell me what is the plastic moment now? Plastic moment is 2 times the elastic moment. Okay, ante so for a same section, its a plastic moment will be twice the elastic moment ante mari carrying capacity ekku unnata leda. See, without considering the plastic moment, when you start design, what happens? Unknowingly your sections will increase in its sizes. Your sections may increase in its dimensions, which makes your member uneconomical. So when you consider your plastic moment, which is twice the elastic moment, so by that your section shows its a maximum moment of resistance where you can design your section under economical way. So that is how shape factor is going to be defined as, which is the ratio of plastic moment to the elastic moment, which is, remember that shape factor is the property of a section which depends only upon the geometry of the cross sections. Shape factor will always vary based on the dimensions or geometry of the cross sections. For example, for the rectangular section, shape factor is different. For circular section, shape factor will be different. So shape factor will just shows you the factor of difference between the plastic moment and an elastic moment. Okay. So by that, shape factor will be always greater than 1. It never be less than 1. Okay. I will try to derive how the shape factor is greater than 1. So now let me show you how to calculate the shape factor. So ఇక్కడ ఒక చిన్న 3 steps ఇచ్చామమ్మా. It's a common steps. Measure the area of the face of the object where the load is being applied. So that is the first step you need to follow to calculate the shape factor. Second, measure the cumulative area of all faces that can bulge. Ante when it is subject, when it gonna bulge, when it is under plastic zone, member shows its permanent deformation when the load is applied. Okay, that is the second one what I need to calculate. In the first one, I need to calculate the original area when it is being applied. The second one, I need to calculate the cumulative area when it is under bulge. And the next one is divide the area of the load face by the area of the bulge face. So what is this? Divide the area of the load face by the area of the bulge face. Area of the load face is nothing but what? When it is under elastic. Area of the bulge face is what? When it is under plastic. Okay. So the dividend of these two will give the shape factor difference. Okay. So this is how the general calculation of the shape factor can be shown. So before explaining about the plastic section modulus and shape factor, how to calculate, let me show you the one picture. One diagram. So this is a bending stress diagram of a common rectangular section. Okay. See, what is this? This is the bending stress diagram where your stress is maximum at the outmost layer above the neutral axis, maximum stress below the maximum stress at the outmost layer below the neutral axis. So if you take a simply supported beam, below the neutral axis will be under tensile zones and above the neutral axis will be under compression zone, isn't it? Yeah, sorry. I would like to stop at the point where I need to explain. Yeah. So now please try to observe carefully. So this is the bending stress diagram of a rectangular section, right? So this is the compression force above the neutral axis where all these fibers will be under compression and this will be under tensions, right? So this is the pure bending equation. F stands for bending stress is equal to moment of resistance into depth from the neutral axis, which is C by moment of inertia, right? So what is this? This is the tensile force and this is the compression force. Tensile forces makes these layers under elongate. Compression forces makes these layers under compression. Understand? Idantha meeku strength of materials lone explain chesuntam, right? So now try to implement these to calculate the plastic section modulus along with the shape factor. Okay. So let me close the video and coming to our picture. So now in the video I have seen the graph which was like this. How we seen the graph? We have seen the graph like this, isn't it? Yeah, right. So this is how the stress strain curve of a rectangular section which is under elastic analysis. Then what is this? So this is also a stress strain curve but which is under plastic analysis. So this is the plastic stress strain curve of a rectangular beam which is under bending. This is an elastic stress strain curve elastic bending stress diagram which is under elastic analysis. Okay, so this was modified into like this. So why? Because your member is under plastic zone. So let me read out all the parameters over here. Sigma y is nothing but yield stress. C is nothing but compression force. Okay, this is the compression force which is equal to, what is the force formula? Force is equal to area into stress, isn't it? What is area? See, when the force is exactly at the center of this portion, what will be the area? The area will be A by 2. A by 2 is the area which is acting at the half of the depth of this particular portion. ఈ portion లో half of the depth లోనే ఈ compression force act అవుతుంది. By that area is half of the area, A by 2. And sigma v is nothing but stress. In the same way, come to the below the neutral axis. So this is the tensile force. Where the tensile force is acting? Tensile force is also acting exactly at the center of this portion, where the area of this portion is A by 2. I mean half of the area, and sigma y is nothing but stress. What is yt? Yt is nothing but depth of tensile force. Yc is nothing but depth of compression force. Right? Clear? Understood? ఇది మీ అందరికి అర్థమైందా? ఇది పిక్చర్. Every parameter is very important. Force is equal to area into stress. Tensile force is equal to area into stress. Why A by 2? Why? Because your force is acting at half of the portion. Let us take this area is A. Then what will be the half of the area? Which will be A by 2. Okay. Now, similarly to this also. So now, moment at which the entire section is under yield stress. And entirely under yield stress, your compression is equal to tension. Isn't it? Then write both are equal. AC into sigma y is equal to AT into sigma y. AC is nothing but what? Area at compression is equal to area at tension. How you can write AC? AC is equal to, why? Because both are having yield stresses. AC is equal to AT. And what is the area at every zone? Which is half of the area, A by 2. Area at compression zone is half, and area at tension zone is also half. AC is equal to AT is equal to A by 2. ikkada varaku మీ అందరికి అర్థమైందా? So this is how it shows how to calculate the plastic section modulus and shape factor. Okay, so please try to understand carefully, amma. So moment at which the entire section is under yield stress, where the both areas at compression and tension is equal, which is A by 2. Okay, right. Next, neutral axis divides cross section into two equal parts. So where your compression force is equal to tension force is equal to what? Both are same. చూడండి ఒకసారి పిక్చర్. A by 2 into sigma y at tension, A by 2 into sigma y at compression. Both are equal, right? So that's why compression is equal to tension is equal to A by 2 into sigma y, right? And coupled due to. So these are the direct forces. Can you tell me what is the coupled? Couple ante ente moment. This force into distance towards the neutral axis. ఎప్పుడు గుర్తుపెట్టుకోండి, always member carry its force towards its neutral axis. Okay, we all know that member always transfers its force towards its neutral axis. So this compression force, okay, acting towards its neutral axis with some distance. What is that? C into yc. What about this tensile force? Tensile force is also towards its neutral axis. What is this distance? T into yt. Okay, like that. So now see here, couple due to. A by 2 into sigma y is equal to A by 2 into sigma y of yc plus yt. What is this yc and yt? Yc is nothing but distance of this compression force from the neutral axis. Yt is nothing but distance of this tensile force from the neutral axis. Clear? అందరికి అర్థమైందా? So that's how force into distance and force into distance. That's how I wrote here A by 2 of sigma y of yc plus yt. So finally I can write this as sigma y of zp. So what do you mean zp over here? This is what the plastic section modulus formula. Okay, so from this plastic stress diagram of a rectangular beam, I have derived a formula where sigma y into zp. What do you mean zp over here? Zp is nothing but A by 2 of yc plus yt. ZP ని ఎలా క్యాలిక్యులేట్ చేస్తున్నామా? ప్లాస్టిక్ సెక్షన్ మాడ్యులస్ plastic section modulus can be calculated as half of the area of the section into depth from the neutral axis to the compression force plus depth from the neutral axis to the tensile force. Okay, this is how the section modulus is going to be calculated. See, your ZP relate to its elastic section modulus. ZP by ZE will always be greater than 1. This is what the shape factor. So here two things I am letting you know. How to calculate plastic section modulus. Plastic section modulus of any section can be calculated with the formula A by 2 of YC plus YT. Okay. What is shape factor? Shape factor is defined as the ratio of plastic section modulus to elastic section modulus, which is always greater than 1. Okay. Now I will show you how to calculate for few sections. Let me take first a rectangular section. Let me show you how to calculate the plastic section modulus and what is the shape factor of a rectangular section. So let's take a rectangular section of width B and depth D. What is half of the depth? D by 2 from the neutral axis, D by 2 from the neutral axis. Now first calculate the section modulus which is under elastic. We all know how to calculate the section modulus under elastic. Z is equal to I by Y. What is I? Moment of inertia. What is Y? Depth from the neutral axis to the outmost layer. What is I of a rectangular section? BDQ by 12. What is Y? From the neutral axis to the outmost layer where the bending stress will be maximum. Neutral axis to the outmost layer where your bending stress will be maximum, isn't it? So that's how your Y is nothing but D by 2. So BD square by 6 is the elastic section modulus of a rectangular section. And coming to plastic section modulus, what is the plastic section modulus formula? From here, A by 2 of YC plus YT. A by 2 of YC plus YT. Chusara? Right. What is A by 2? A by 2 ante entama. What is A? Area. What is area of a rectangular section? B into D by 2 of. What is YC? What do you mean YC? YC ante enti? Depth from the neutral axis to the compression force. Chudandi jagrattaga. I will show you with pointer. This YC and this YT. Okay. Entivi? Ikkada chudandi. This is what YC and this is what YT. Clear? YT and enti ikkada? Distance from the tensile force to the neutral axis. What did you mean YC? Distance from the compression force to the neutral axis. Compression force ekkada act avutundi? Exactly at the half of the depth of the section above the neutral axis. Exactly half of the depth of the area below the neutral axis. Okay. So avi manam ikkada consider chestam. What is the YC distance? YC ekkada act avutunamma? Ikkada. What is this distance? D by 4. Ikkada YT ekkada act avutunamma? Ikkada act avutundi. What is this distance? D by 4. D by 4 plus D by 4 area by 2, which is BD square by 4. This is what the plastic modulus. Clear? So I think you all know till now we all calculated the elastic section modulus which is under elastic consideration. But now the plastic modulus which we are calculating by considering member which is under plastic. Which is under permanent deformation. So the BD square by 4 is the plastic section modulus. So the ratio of plastic section modulus by elastic section modulus is shape factor. Chudandi BD square by 4 by BD square by 6. Enti value 1.5. So 1.5 is the shape factor of the rectangular cross section. Clear? Chala important amma. In many competitive exams, they are just asking what is the value, what is the shape factor of the different sections. Adutar. Lekapothe they may ask you to calculate and put the answer. So you should all know how to calculate the shape factor just by remembering this plastic section modulus formula. Idu okkati meer gurtu pettukondi. So by that you can able to calculate the plastic section modulus of a cross sections which are symmetrical to both the axes. Symmetrical to both the axes ki plastic section modulus calculate cheyadaniki chala simple formula idi. A by 2 of YC plus YT. Okay, just you have to remember YT is nothing but this. YC is nothing but this. Okay, got it? Right. So let me show you another cross section how to calculate the plastic modulus and shape factor. Take a circular section. Let's calculate what is the plastic section modulus. A by 2 of yc plus yt. What is A by 2? What is the area of circle? Pi d square by 4, right? By 2, which gives pi d square by 8 of. What is yc? yc ekkada untundamma? Ee semicircle lo half of the distance. Ee semicircle lo half of the distance. So this distance is yt and this distance is yc, right? So d cube by 6 is the plastic section modulus. And what is elastic section modulus? We all know, I by y. What is moment of inertia of a circle? Pi d power 4 by 64. What is depth? What is the y? D by 2. Why? Because your maximum bending stress will be maximum at the outmost layer from the neutral axis. This E distance and the d by 2, which is pi d cube by 32. Okay, d cube by 6 by pi d cube by 32 and the 1.7. So 1.7 is the shape factor of a circular section. ఓకే చూడండి ఎంత సింపుల్గా క్యాలిక్యులేట్ చేయొచ్చు. ఇక్కడ మళ్ళీ మీరు చెప్పండి అమ్మా, వాట్ ఈస్ ద మీనింగ్ ఆఫ్ ఏ షేప్ ఫ్యాక్టర్? వాట్ ఈస్ ద మీనింగ్ ఆఫ్ ఏ షేప్ ఫ్యాక్టర్? సో ఇఫ్ యూ సీ ద stress strain curve of any member, so this is the elastic section modulus and this point is called plastic section modulus. Your plastic section modulus will always be 1.7 times of the elastic section modulus anta. అర్థమవుతుందా? ఇక్కడ సెక్షన్ మాడ్యులస్ ఎంత ఉంటుంది? 1.7 times of elastic section modulus ఉంటుంది plastic section modulus value. Okay, అంటే in terms of section modulus we can tell like this. In terms of moment చెప్పాలి అంటే your plastic moment of resistance will be 1.7 times the elastic moment of resistance from this point. అంత ఎక్కువ ఉంటుంది. Okay, so that also you can able to explain. So let me show you for another cross section. So for the triangular cross section, what is the triangular cross section shape factor? So this is a elastic section modulus I by y. What is I? Triangle యొక్క moment of inertia ఎంతమా? bh cube by 36. What is the depth from the neutral axis? As your triangle is unsymmetrical to both x axis, your depth is 2h by 3 from here and h by 3 from here. Kada? The maximum value, this is the maximum depth. That's why I am taking 2h by 3 for calculating the elastic section modulus instead of taking h by 3. Okay, right. So z is equal to bh square by 24, which is a elastic section modulus. Okay, and what is plastic section modulus? A by 2 of yc plus yt. So let's calculate what is yc and yt of this triangle. చూడండి ఇక్కడ చాలా క్లియర్ గా మెన్షన్ చేశారు. So this is your yc, which is the half of this overall depth, and this is yt, which is half of this overall depth. Okay, so once you calculate these two and area by 2 will use the plastic section modulus. The ratio of plastic section modulus to elastic section modulus is 2.346 is the shape factor of a triangle. Chusara? So this is how we need to calculate the shape factors for different cross sections. Okay, there. And let me show you shape factor for different sections like this. Shape factor for square is 1.5. Shape factor for diamond is 2. Very important, at least you will get one question out of this table in any competitive exam like AE, AEE, JE, SSC exams. Okay, in GATE they may not ask such a simple question, but in GATE they may ask you to calculate the shape factor for the given section. The shape factor for the circular section 1.7, just now we calculated. The shape factor for hexagon is 1.6. Okay, the shape factor for triangular horse glass is 1.33. The shape factor for thin walled circular tube is 1.27. So and for a thick walled circular tube you have to calculate with this formula. For hollow rectangular section you have to calculate with this formula. For C section you have to calculate with this. So this is how you need to calculate. Here I want to tell you one important note. Please all of you remember the maximum shape factor available for a section which is a diamond section. Diamond section ki shape factor eppudu maximum value untundi. which is 2. చూడండి 1.5, 1.7, 1.6, every section is having less than 2. The maximum shape factor is for diamond cross section కి ఎక్కువ షేప్ ఫ్యాక్టర్ ఉంటుంది. ఓకే, ఎక్కువ షేప్ ఫ్యాక్టర్ ఉంది అంటే అర్థం ఏంటి? దిస్ మెంబర్ ఈజ్ హ్యావింగ్ maximum plastic moment of resistance అని అర్థం, అంతే కదా. ఈ మెంబర్కి ఎక్కువ షేప్ ఫ్యాక్టర్ ఉంది అంటే ఏంటి అంటే డైమండ్ సెక్షన్స్ ఆర్ హ్యావింగ్ మోర్ రెసిస్టెన్స్ టువర్డ్స్ మూమెంట్. అర్థమవుతుందా? సో దట్ ఈస్ ద మీనింగ్ ఆఫ్ హ్యావింగ్ ఎ మోర్ షేప్ ఫ్యాక్టర్. ఓకే, రైట్. సో లెట్ మీ కంటిన్యూ విత్ నెక్స్ట్ థింగ్. Sorry. Yeah. So now coming to the collapse mechanism. See how these plastic hinges are very important for your plastic analysis, and how this plastic collapse mechanism is important in designing your structures. Right. See, collapse mechanism ante entante which is known as a beam mechanism. So here I am showing an example which is a determinate beam. What do you mean this? This is a simply supported beam. Simply supported beam is a determinate beam. Yes or no? Simply supported beam, cantilever beam, overhang beam, they are all comes under the determinate beams. See, determinate beams and frames collapse after first plastic hinge. ఎప్పుడు సింప్లీ సపోర్టెడ్ బీమ్స్ ఎప్పుడు కొలాప్స్ అవుతాయో తెలుసా? ఆఫ్టర్ ఫార్మింగ్ ఇట్స్ ప్లాస్టిక్ హింజ్, దెన్ ఇట్ స్టార్ట్స్ కొలాప్స్. వెరీ 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 ఇంపార్టెంట్. ఓకే, so when the simply supported beam collapse after forming plastic hinge within the beam, then member starts collapse after first plastic hinge form. Simply supported beam lo enduku plastic hinge center lo form ayindi? Why? Because in a simply supported beam subjected to concentrated load exactly at center, the maximum bending moment will be at center. So when the maximum bending moment at center, member will deflect like this. So this is the point where the plastic hinge forms and the beam will fail first at the center. అంతేనా? మీరు ఎప్పుడైనా బీమ్స్ని ఎప్పుడైనా మీరు ఫ్లక్చురల్ టెస్ట్ చేశారా? when you do beam test under lateral force, okay, so you can see the first failure in the beam exactly at center. So why? Because at center the plastic hinge forms and it will fail. Okay, and let me show you for fixed beam, for indeterminate beam. Fixed beam is an indeterminate beam. Indeterminate beams and frames more than one plastic hinge to develop mechanism. See, in fixed beam, where are the plastic hinges forms? When a fixed beam is subjected to load, your plastic hinges will forms at three points. Ekkada? At supports and at center. Okay, మీరు కావాలంటే చూడండి. So what is the bending moment of this? Can you able to draw? What is the bending moment of simply supported beam subject to point load? So this is the bending moment, right? In the same way, what is the bending moment of this fixed beam? ఈ ఫిక్స్డ్ బీమ్ బెండింగ్ మూమెంట్ ఎలా ఉంటుందమ్మా? Right? So this is the bending, this is the bending moment of the fixed beam when it is subjected to constant load at center. So see, where are the plastic hinges formed? Plastic hinges formed at supports and at center. So there are 3 plastic hinges formed. If more than one plastic hinge formed to develop mechanism, ఇక్కడ ఒక మెకానిజం డెవలప్ అవ్వాలి అంటే more than one plastic hinge form అవ్వాలి, then only fixed beam will fail. Okay, when fixed beams, indeterminate beams will fail not with one plastic hinge. It should form more than one plastic hinge to fail for the load. కానీ ఇక్కడ సింప్లీ సపోర్టెడ్ బీమ్స్లో ఏమవుతుంది? ఒక్క ప్లాస్టిక్ హింజ్ ఫామ్ అయితే చాలు, ఇట్ గోస్ అండర్ ఫెయిల్యూర్. బట్ ఇన్ ఫిక్స్డ్ బీమ్స్ లైక్ ఇండిటర్మినేట్ బీమ్స్ యూ షుడ్ రిక్వైర్ మోర్ దాన్ వన్ ప్లాస్టిక్ హింజ్ టు డెవలప్ మెకానిజం. ఓకే, సో చూడండి ఇక్కడ చాలా ఇంపార్టెంట్ నోట్ పాయింట్స్ ఉన్నాయి. ప్లాస్టిక్ హింజెస్ డెవలప్ ఎట్ ద ఎండ్స్ ఫస్ట్. ఎప్పుడు ప్లాస్టిక్ హింజెస్ సపోర్ట్స్ దగ్గర ఫామ్ అవుతాయి, నథింగ్ బట్ ఎండ్స్. దెన్ beam becomes a simple beam. When the plastic hinges forms at support, you can say that your beam is becoming a simply supported beam. Avuna? What do you mean hinge? Hinge always allows rotation. Okay, that is how this hinge making your beam into a simply supported beam. రైట్, ఎప్పుడైతే మీకు హింజెస్ సపోర్ట్ దగ్గర ఫామ్ అయిందో మీ బీమ్ సింప్లీ సపోర్టెడ్ బీమ్ అయిపోయింది. వెన్ బీమ్ బికమ్ సింప్లీ సపోర్టెడ్ బీమ్, దెన్ యువర్ బీమ్ స్టార్ట్స్ ఫెయిల్. సో బీమ్స్ బికమ్ ఏ సింప్లీ సపోర్టెడ్ బీమ్, ప్లాస్టిక్ హింజెస్ డెవలప్స్ ఎట్ సెంటర్ అండ్ బీమ్ కొలాప్స్. సో దిస్ ఈస్ వేర్ ద బీమ్ కొలాప్స్ ఇన్ ఇండిటర్మినేట్ బీమ్స్. చాలా ఇంపార్టెంట్ అమ్మా. ఓకే, మీకు అర్థం కాకపోతే నేను మళ్ళీ చెప్తాను. దిస్ కాన్సెప్ట్ ఈస్ వెరీ వెరీ ఇంపార్టెంట్. ప్లీజ్ ట్రై టు అండర్స్టాండ్ కేర్ఫుల్లీ. In determinate beams, if one plastic hinge forms, it goes under collapse. In indeterminate beams, plastic hinges always forms at supports. Then that beam becomes a simply supported beam. Then it will fail under plastic hinge which is developed at center. అర్థమవుతుందా? అంటే ఇక్కడ మోర్ దాన్ వన్ హింజ్ ఫామ్ అయితే ఫెయిల్ అవుతుంది, సింప్లీ సపోర్టెడ్లో ఒక హింజ్ ఫామ్ అయినా ఫెయిల్ అయిపోతుంది. ఓకే, సో దట్ ఈస్ ద డిఫరెన్స్ బిట్వీన్ ఇండిటర్మినేట్ బీమ్స్ అండ్ డిటర్మినేట్ బీమ్స్. ఓకే, సో లెట్ మీ షో యూ అనదర్ ఇండిటర్మినేట్ బీమ్ విచ్ ఇస్ ద ప్రాపర్డ్ క్యాంటిలివర్ బీమ్. సో దిస్ ఇస్ ద ప్రాపర్డ్ క్యాంటిలివర్ బీమ్. One end is fixed, other end is pinned. Let me show you how this is going to fail. In indeterminate beam, something like this, more than one plastic hinge to develop mechanism. చూడండి, ఇది కూడా ఇండిటర్మినేట్ బీమే. ఇండిటర్మినేట్ బీమ్ లో కూడా ఒక ప్లాస్టిక్ హింజ్ తో ఫెయిల్ అవ్వదు ఎప్పుడు. ఇఫ్ ఇట్ ఫార్మ్స్ మోర్ దాన్ వన్ ప్లాస్టిక్ హింజ్, దెన్ ఇట్ స్టార్ట్స్ ఫెయిల్యూర్. సి ఇన్ ప్రాపర్ క్యాంటిలివర్ బీమ్, ఫస్ట్ ప్లాస్టిక్ హింజ్ ఎక్కడ ఫార్మ్ అవుతుంది? ఎట్ సపోర్ట్. ప్లాస్టిక్ హింజ్ డెవలప్ ఎట్ ఫిక్స్డ్ సపోర్ట్ ఫస్ట్. beam comes a simple beam, beam becomes a simple beam. Plastic hinge develops at center, beams collapse. ఓకే, సో అర్థమవుతుందా? ఇక్కడ ప్రాపర్డ్ క్యాంటిలివర్ బీమ్ లో ఫస్ట్ సపోర్ట్ దగ్గర హింజ్ ఫామ్ అవుతుంది అండ్ ఇట్ విల్ మేక్ బీమ్ ఇంటూ ఏ సింప్లీ సపోర్టెడ్ బీమ్. దెన్ hinge forms at center due to the concentrated load and then it will collapse. Clear? So that is how the hinges forms in determinate and indeterminate beam and where it is subjected to failure. Okay, so very very important amma, right? And let me show you how the panel mechanism or a sway mechanism takes place in a frames. Ippudu varaku meer em chusaru? So till now you have gone through the beams like determinate beams and indeterminate beams. Now we will see about the structures, like the framed structures, how it gonna fail under mechanisms. See, due to dead loads and live loads and due to wind loads and earthquake loads like this lateral forces, the internal forces develops in the members. Okay, so I can say these loads may be the dead loads or live loads, and these loads or maybe the wind loads or earthquake loads which are lateral to the structure, and these are lateral to the longitudinal of the member. Okay, so these forces makes member to react with its internal forces developed in the structure. Let me show you how the internal forces develops in the member. So let us take this as two-dimensional structure and the internal forces developed in the member like this. Okay, before bending or before collapsing, member will have a tendency to show its internal forces in terms of moment, in terms of horizontal reaction, in terms of a vertical reaction. Okay, so ఎప్పుడైతే మెంబర్లో క్రాక్ వచ్చింది అనుకోండి, దాంట్లో ఈ మూడిట్లో ఏది ఫస్ట్ లాస్ అవుతుందో తెలుసా? మెంబర్ విల్ లూజ్ ఇట్స్ మూమెంట్ and it will become a hinge formation at that particular point. Okay, so when it is failing, when it have a crack, it lose its. John, I'm telling repeatedly, still some of you haven't received the notes daily wise. After the class, just ping me. Okay, yeah, don't worry guys, every notes will be shared by John, okay, or Srinivas. So they are my supporters, so definitely they will share you. If they are not able to share, please ping me through WhatsApp. Definitely I will share you each and every part of the notes which I am delivering through online. Okay, don't worry for the notes. Okay, right. See, this is how the internal forces developed in the frame structure. So when the beam or a column will fail, first crack form అయింది అనుకోండి, it lose its moment and there is a possibility of plastic hinge formation at that particular point. So it may be at a span, in between the span, or it may be at the joint దగ్గర కూడా ఫామ్ అయ్యే ఛాన్స్ ఉందన్నమాట. ఓకే, సో that's how the framed structures are going to have the plastic hinges. Okay, so this is the gable mechanism. In gable mechanism, so ఈ frame కి మీరు డిఫరెన్స్ చూస్తున్నారు కదా. So this is a portal frame and this is a gable frame. Okay, and as I told you, the method of plastic analysis was happened by with the equilibrium method and the kinetic or mechanism method. Okay, this already discussed. Yeah, so this is very important. Please try to have a snapshot or keep this in mind when you are studying the plastic analysis. These points are very important. మీరు గేట్లో అటెంప్ట్ చేసేటప్పుడు కూడా while solving plastic analysis problems for calculating the failure mechanism load or whatever it is, so these are important. చూడండి, the plastic hinges ఎక్కడ ఫామ్ అవుతాయి అంటే at the point of maximum moment. ఏ బీమ్కి అయితే or any member where it is having a maximum moment, at that point there is a possibility of plastic hinge. Sorry, yeah, see, at the point of maximum moment. So let us take the fixed beam lo maximum moment ekkada untundi? Moments will be maximum at support, isn't it? At maximum support the plastic hinges will form, avuna kada? Yes, at the connection involving change in geometry. What do you mean that? At the connection involving change in geometry ante, so when the section is changing in its cross section, I will show you with some diagrams. Okay, so let me use a pen over here. So first point ki chudamma. So let me take a cantilever beam, right? So where will be the maximum moment? Maximum moment will be at support. At this support plastic hinge will form first. Okay, right. At the connection involving change in geometry, is దీనికి related. At the connection involving change in geometry అంటే, so let me take a frame like this. Okay, see, this column will have maximum size than this. ఎందుకు? Obvious గా we know bottommost columns will carry more loads than the first floor column, right? So by that you can reduce the cross-sectional area of this column, right? So ante enti, at this connection there is a change in geometry in terms of its cross-section. So at this joint there is a change in terms of its geometry and a cross-section change అవుతుంది కాబట్టి ఇక్కడ plastic hinge కూడా ఫామ్ అవుతుంది. ఓకే, అంటే at the connections which is involving change in geometry there is a possibility of plastic hinge formation here. ఇక్కడ plastic hinge ఫామ్ అవుతుంది. Next, under the concentrated load ante, so let me take a simply supported beam like this. At concentrated load plastic hinge form avutundi. Okay, at every concentrated load there will be a possibility of plastic hinge. Next, at the point of zero shear in span loaded by uniformly distributed load. Can you tell me, at the point of zero shear in span loaded by uniformly distributed load, let me take a beam which is having a uniformly distributed load. Uniformly distributed load for a simply supported beam. చూద్దాం, what is bend moment diagram? What is the bend moment diagram for simply supported beam subjected to UDL load? Where is the cursor? Yeah, sorry, isn't it? So this is the bend moment diagram. At this bend moment diagram, at the point of zero shear in span, zero shear ante, so the maximum bend moment will be here, right? Okay, and what is the shear force diagram for this? This is the shear force diagram. And this is the bending moment diagram. ఇప్పుడు చూడండి, at the point of zero shear in the span. ఇప్పుడు ఈ span లో zero shear ఎక్కడుందమ్మా? So this is the point where the zero shear there. At this point, due to uniformly distributed load, plastic hinge will form. అర్థమవుతుందా? Right? So these are the different locations where the plastic hinges forms in the beams. Right? Clear? అందరికి అర్థమైందా? So do you want me to show with a different color over here? Yeah. So this is the plastic hinge formation. And this is the point where plastic hinge will form. And this is the point where the plastic hinge form. And this is the point where the plastic hinge form. Okay. So like this. This is what we need to understand, how the plastic analysis and where the plastic hinges forms when it is subjected to its maximum load. Okay. So which we are considering it as an ultimate load. Right? Right. So next, go to the next one. Determination of collapse load. How to calculate the collapse load. So let me show you few examples how to calculate the collapse load. What do you mean collapse load? At what load your beam will have a formation of plastic hinge and where it is going to fail. At what load it is going to fail. అనేది మనం calculate చేస్తాం. That is what the determination of the collapse load. So this is very, very important for gate point of view. So let me show you for a few examples. So first, simply supported beam. So simply supported beam subjected to concentrated load at center, and this is the bending moment diagram. And the plastic hinge form ఎక్కడ జరుగుతుందమ్మా? Simply supported beam లో there is a possibility of only one plastic hinge that will form exactly at the concentrated load point. అంటే ఇది plastic hinge point. అవునా? Right. And what is this? This is the bending moment diagram. And what is the maximum bending moment diagram of a simply supported beam subject to point load at center? WL/4. మనందరికి తెలిసిందే కదా. By using equilibrium method, the maximum bending moment at this particular point is WL/4. WU అంటే ఏంటి ఇక్కడ? What is W? W is nothing but ultimate load. Ultimate load into length of member by 4. Okay? Right. And now I want to calculate the collapse load. Okay? ఇప్పుడు WU ఎలా క్యాలిక్యులేట్ చేయాలి? 4 into MP by L. Understood? 4 into MP by L. So what is MP? MP is nothing but the maximum plastic moment which it carrying at this particular point. Okay? Into 4 by L. How to calculate the plastic moment? Can anyone tell me how to calculate the plastic moment? What is the plastic moment formula? Plastic moment is equal to plastic section modulus into bending stress. Okay? So you know the bending stress and you know the plastic section modulus of this member, and this is how you can calculate the plastic moment. Plastic moment into 4 by length will use the collapse load of your simply supported beam. Okay? So this is very important. So please try to remember this formula to calculate the collapse load of a simply supported beam when it is subjected to concentrated load at center. Okay? Next. With another method. So identi? This is equilibrium method. Okay? By using another method, so let me calculate how to calculate the collapse load with the help of an virtual work method. Virtual work method can also be called as a kinetic method or mechanism method అని కూడా అంటారు. So what is this virtual work method? చూడండి, వర్చువల్ వర్క్ మెథడ్ ద్వారా ఈక్విలిబ్రియం మెథడ్ ద్వారా రెండింటి ద్వారా మనకి సేమ్ ఫార్ములానే వస్తుంది, విచ్ ఇస్ 4mp/L. ఇక్కడ కూడా చూడండి 4mp/L. You can make use of any method to calculate the collapse load. Okay? So let us see how to calculate the virtual work method. WE is equal to WI. Okay? So what is WE? W is nothing but load at equilibrium condition and load at end condition. So WU of L/2. So you could show me what is WU. WU is the ultimate load which is acting on the beam into what? Into this distance. So what is this distance? So half of the distance is L by 2. Okay, and the angle is theta. Okay na? Antena? ఈ డిస్టెన్స్ ఎంత WU into this, which is L by 2 into theta, is equal to MP into 2 theta. What is MP into 2 theta? MP into 2 theta is the resistance. Okay, so then only your member will be under equilibrium. So MP into 2 theta, what is MP? MP is nothing but plastic moment which is happening from the plastic hinge. MP into 2 theta, right? W into L by 2 into theta is an applied moment. MP into 2 theta is the resisting from the plastic hinge. From this, what is WU? W is the ultimate load. W is equal to 4 into MP by L. So this is the virtual method. మనం వర్చువల్ మెథడ్ ద్వారా చేయొచ్చు ఆర్ ఈక్విలిబ్రియం మెథడ్ ద్వారా కూడా చేయొచ్చు. ఓకే, సో హియర్ యూ హ్యావ్ టు రిమెంబర్ దిస్ థింగ్ టు క్యాలిక్యులేట్ ద ఈక్విలిబ్రియం థింగ్. One is applied, one is the resistance one. Okay, sorry, clear? So this is the virtual work method. So let me show you another example. అప్పుడు ఇంకా కొద్దిగా బాగా అర్థమయ్యే ఛాన్స్ ఉంటుంది. ఫిక్స్డ్ బీమ్ with UDL load. Okay, see, fixed beam with UDL load, how many plastic hinges will form? First, plastic hinges will form at supports, and then by making your beam into simply support, and then the next plastic hinge will form at center. Okay, M center is equal to M end. ఇక్కడ కూడా మీకు అర్థమవుతుంది. M center ఏంటమ్మా? What is the maximum bending moment when fixed beam is subjected to UDL load? WL by 24. Okay, so what is at ends? WL square by 12, which is greater than at center. Avuna kada, right? So WL by 24 is at center of a beam, and WL square by 12 is at ends. So hence plastic hinges will develop at the ends first, and this is how the beam action takes place, and this is how you need to calculate the virtual method. Okay, so first we will try to use the equilibrium method to calculate the collapse load of this fixed beam, right? చూడండి ఎలా క్యాలిక్యులేట్ చేస్తాం. ఫస్ట్ ఈక్విలిబ్రియం మెథడ్. 2MP is equal to, what is 2MP? 2 of the plastic moments is equal to WL square by 8. Simply supported beam subjected to UDL load. What is the maximum bending moment at center? WL square by 8. అవునా కదా? ఎందుకు WL square by 8 అంటున్నాను? Because when the plastic hinges formed at fixed support, your beam is going to be a simply supported beam. By that simply supported beam subjected to UDL load, what is the maximum bending moment? WL square by 8. Okay, so 2MP is equal to WL square by 8. Then WU is equal to 16MP by L square. So 16MP by L square is the collapse load of a fixed beam subjected to UDL load. Okay, you can make use of equilibrium method also, right? ఇక్కడ 2MP ఎందుకు? మీరు ఒకసారి సింప్లీ సపోర్టెడ్ బీమ్ చూడండి. You took only MP. Why single MP? Why? Because you are having only one plastic hinge which formed first. Okay, why here I took 2MP? 2MP ఎందుకు తీసుకున్నాను ఇక్కడ? Because there are two plastic hinges which are formed at supports, right? ఇక్కడ ఒక plastic hinge form అయింది, ఇక్కడ ఒక plastic hinge form అయింది. Because of two plastic hinge formations, you took 2MP, which will be equal to WL square by 8. Then what is the collapse load? Collapse load అంటే ఏంటి? Ultimate load. WU is equal to 16MP by L square. చూడండి, మీ అందరూ చూడండి, ఏది సింపుల్ మెథడ్? ఈక్విలిబ్రియం మెథడ్ చాలా ఈజీగా ఉంటుంది. వన్ ఈక్విలిబ్రియం మెథడ్ ఈజ్ ఈజీ వెన్ యూ నో హౌ టు క్యాలిక్యులేట్ ద మ్యాక్సిమం బెండింగ్ మూమెంట్. మీ అందరికీ మ్యాక్సిమం బెండింగ్ మూమెంట్ ఫార్ములాస్ తెలిసి ఉండాలి. దెన్ ఓన్లీ యూ కెన్ ఏబుల్ టు క్యాలిక్యులేట్ కొలాప్స్ లోడ్స్ విత్ ద హెల్ప్ ఆఫ్ అన్ ఈక్విలిబ్రియం మెథడ్. ఓకే, అది చాలా సింపుల్. అదే వర్చువల్ వర్క్ మెథడ్కి రండి. వర్చువల్ వర్క్ మెథడ్లో ఏంటి? సో ఫస్ట్ యూ హ్యావ్ టు నో ద మెకానిజం. ఈ మెకానిజం చూడాలి. 2 of MP, సో విచ్ ఇస్ WU into L by 2. దీనికి డయాగ్రామ్ మనం డ్రా చేయాలి. how the member is going to be failed అని ఈ యాంగిల్స్ నుంచి మనం డ్రా చేస్తాం అనమాట. సో హియర్ వన్ యాంగిల్, ఓకే. సో హియర్ అనదర్ యాంగిల్ which is theta. So same like simply supported, you will have 2 theta from here. So with this virtual method we can able to calculate, and finally the formula will be same. చూడండి ఈ ఫార్ములా రెండు సేమే from equilibrium method and from the virtual work method. So 2 of WU into L by 2 distance. ఎందుకు L by 2 distance? ఇక్కడే మీరు చూడొచ్చమ్మా. చూడండి ఇక్కడ పిక్చర్ ఉందా, రైట్. వర్చువల్ వర్క్ మెథడ్ చూడండి దీంట్లో. సో లెట్ మీ ఎరేజ్ దిస్ అండ్ షో యూ. సారీ, యా, రైట్. సో హియర్ యూ క్యాన్ సీ theta and 2 theta, right? 2 times of WU L by 2, WU into L by 2. ఎంత ఈ డిస్టెన్స్? L by 2 distance. So this distance is L by 2. Okay? And this distance is also L by 2. 2 times of WU into L by 2. Why 2? 2 ante enduko? There are 2 hinges. This is one hinge and this is another hinge. So 2 of WU into L by 2 of 0 plus L by 2 of this theta. So which is half of the whole member, okay. ఈ డైరెక్షన్లో which is W2 into L by 2, and ఇక్కడ L by 2 into theta which is half of the section, right? So which gives MP of theta plus 2 theta plus theta. అంటే plastic moment which is happened at center of theta and 2 theta. So this is a summation of these 3, okay. So then WU is equal to 16 times of MP by L square. So this is how the virtual method will happen based on this formula where your M center is equal to M ends. For calculating your virtual work method, you have to use this. So there the forces at ends and the forces at center. Okay, when you equate these two, with that you can able to calculate this value. Yeah, not considered middle one ante I already told you in fixed support, first hinges will forms at supports only. You have to consider those two which creating member to fail. So that is the reason why I am considering only 2 hinges which is making your member to collapse. Okay. So అందువల్ల 2 hinges నే నేను కన్సిడర్ చేస్తున్నాను which are forming at the support conditions. అర్థమవుతుందమ్మా? ఎప్పుడు ఫిక్స్డ్ సపోర్ట్స్ ఉన్నాయనుకోండి, సపోర్ట్స్ దగ్గర ఉన్న hinges ని కన్సిడర్ చేయాలి for calculating the collapse load. Okay, if there is no hinge at supports, if there is only hinge within the span, then that hinge is going to be considered to calculate the collapse load. Okay, that's the only difference, right? So let me show you for another example which is fixed beam with the point load. ఇందాక మనం UDL load చూసాం కదా. So let's see for the point load. See, point load also there are 2 hinges at support, 1 hinges exactly at the point load, right? So what is the bending moment diagram? మనకు తెలిసి bending moment diagram will be like this, and whatever the moment happens here, this is plastic moment and these are also a plastic moments, right? Okay, equilibrium method చూడండి ఒకసారి. ఇక్కడ కూడా 2MP is equal to, why 2MP? 2 plastic moments, plastic hinges which are formed at supports is equal to WL by 4. What is WL by 4? Simply supported beam subjected to point load at center. What is the maximum bending moment? WL by 4. Sir, ikkada fixed beam kada? No. As I already told you, when in plastic analysis at fixed beam, hinges will form first at support. It makes member to have a hinge. ఇక్కడ హింజ్ క్రియేట్ చేస్తుంది. ఇక్కడ హింజ్ క్రియేట్ చేస్తే ఈ బీమ్ ఏ బీమ్ అయిపోయింది? సింప్లీ సపోర్టెడ్ బీమ్ అయిపోయింది. సింప్లీ సపోర్టెడ్ బీమ్ సబ్జెక్ట్ టు పాయింట్ లో అయితే మాక్సిమం బెండ్ మూమెంట్ ఎంత? WL by 4. ఓకే, సో దెన్ వాట్ ఈస్ WU వాల్యూ? 8MP by L. చూడండి ఎంత సింపుల్ ఉందో. సో దిస్ ఈస్ హౌ ఐ థింక్ for a competitive exam point of view you can make use of equilibrium method if you are not aware about virtual work method. Okay, so ikkada chusara, so 2 mp, again I took only 2 plastic hinges which are formed at support is equal to maximum bending moment. Okay, so then ultimate load is equal to 8 mp by L. And coming to your virtual work method, WU చూడండి, WU moment, WU into L by 2 times of theta is equal to mp of theta plus 2 theta. Okay, so then finally how to calculate WU? WU is equal to 8 mp by L. Okay, so this is how you need to calculate. Here what is this two? This is nothing but this. WE is equal to WI. Okay, forces at ends is equal to forces at center. అలా మనం ఈక్వేట్ చేసి దిస్ వర్చువల్ వర్క్ మెథడ్ ద్వారా క్యాలిక్యులేట్ చేస్తాం. బోత్ విల్ బి సేమ్. ఓకే, బోత్ ద వాల్యూస్ విల్ బి సేమ్. సో దిస్ ఈస్ ఫర్ ఫిక్స్డ్ బీమ్ విత్ పాయింట్ లోడ్. సో అనదర్ ఎగ్జాంపుల్ we can see a fixed beam with eccentrical point load. So what do you mean eccentrical point load? Where the load is not at center. Okay, so see, when the load is not at center, distances will be not equal A, B. Can you tell me what is the maximum bending moment when simply supported beam is subjected to point load at some eccentrical distance? ఎవరైనా చెప్తారమ్మా ఎంత? This is the bending moment and this maximum bending moment value is W AB by L. అవునా? Right? Yeah. So ఇక్కడ కూడా చూడండి, in equilibrium method. So as it is a fixed beam, how many hinges will form? This is one hinge at support. This is another hinge at support. Okay, 2 hinges. 2 into mp is equal to 2 plastic hinges form a 2 into mp is equal to WU into AB by L. WAB by L is the maximum bending moment when a simply supported beam is subjected to point load at some eccentricity. Okay, ఇది మనకు తెలిసిందే. So then what is WU? Ultimate load is equal to 2 mp into L by AB. Easy కదా? అందుకే మీ ఇష్టం అమ్మా. If you are very flexible with the equilibrium method, you can follow the equilibrium method to calculate the collapse loads. Okay, so you can see even the virtual work method also. Virtual work method కొద్దిగా అర్థం అవ్వడానికి టైం పడుతుంది. Why? Because you have to go through with the what are the end conditions. So what is the end moments and what is the center moments, అది మీకు తెలియాలి. సో చూడండి, వర్చువల్ వర్క్ మెథడ్ ద్వారా క్యాలిక్యులేట్ చేస్తే ఫార్ములా వాల్యూ ఏమొచ్చిందో, 2 mp into L by AB. ఇక్కడ కూడా ఇది 2 mp into L by AB. చూడండి, సేమ్ వాల్యూసే వచ్చాయి. సో యూ కెన్ యూజ్ ఎనీ మెథడ్. ఈక్విలిబ్రియం మెథడ్ వాడచ్చు, ఇది వాడచ్చు. ద ఓన్లీ డిఫరెన్స్ ఈస్ for using equilibrium method, you should be very familiar with all bending moment formulas. Okay, for all types of beams. For using virtual work method, the only thing is you should know where the where the slopes will form in the beam when it is subjected to load. Okay, అర్థమవుతుందా? ఇక్కడ చూడండి, W into A into theta 1. So this is the first angle and this is the second angle. So in earlier cases, angles are equal kada. ikkada angle anta undo, ikkada angle ante. So the twice angle is 2 times of theta ikkada. Kani ikkada point is not at center. Point is with some eccentricity. By that the slope at this point is different, slope at this point is different. By that this is theta 1, this is theta 2 and this is theta 1 plus theta 2. Okay, and what is theta 1? Theta 1 is equal to B by A of theta 2. Okay, right. So now WU into theta 1 into A is equal to, so this is applied moment and the resisting moment enti mp of theta 1 plus theta 2 plus theta 1 plus theta 2. చూడండి, theta 1 plus theta 1 plus theta 2 plus theta 2 మొత్తాన్ని సాల్వ్ చేయండి, you will get the value. Right? చూడండి ఎంత ఈజీగా ఉందో. So this is the virtual method. Virtual method కూడా ఈజీయే. The only thing is you should be able to locate all these angles first based on its bending nature. Okay, and you should identify the plastic hinges where it will be formed. Okay, so based on that, ఇది అన్న మీరు యూజ్ చేయొచ్చు, ఈ మెథడ్ అన్న యూజ్ చేయొచ్చు. Clear? So 4 examples we have gone through how to calculate. And let me show you another example, which is a propped cantilever with point load at mid-span. A cantilever beam subjected to point load at mid-span in a propped cantilever beam. So for this, we should calculate the collapse load. So let's see how to calculate the collapse load for this. Go with an equilibrium condition. Okay. Cantilever beam subject to point load at here. ఇందాక అనుషా రెడ్డి అడిగింది సార్ ఇందాక ఫిక్స్డ్ బీమ్లో 2 hinges 2 పిన్ హింజ్ ఫార్మ్సే తీసుకున్నాం కదా. ఇక్కడ చూడు ఎన్ని సపోర్ట్స్ ఉన్నాయమ్మా, ఒక సపోర్టే ఉంది. ఒక సపోర్ట్ ఉంది కాబట్టి ఒక ప్లాస్టిక్ హింజే ఫామ్ అవుతుంది ఫస్ట్. దట్స్ ద రీజన్ వై ఐ టుక్ ఓన్లీ ఫస్ట్ 1 plastic hinge ఫర్ క్యాలిక్యులేటింగ్ ద ఈక్విలిబ్రియం కండిషన్. ఓకే. And one more, as it is propped cantilever, it is not a fixed support. That's why it will form only half plastic hinge here. అందుకని ఇక్కడ 0.5 MP తీసుకున్నాను. చూసారా? ఒకటే గుర్తమ్మా, ఫిక్స్డ్ సపోర్ట్ ఉంటే యూ క్యాన్ టేక్ కంప్లీట్ ప్లాస్టిక్ హింజ్ వాల్యూ. పిన్ ఉంటే లైక్ పిన్నెడ్ సపోర్ట్ ఉంటే యూ షుడ్ టేక్ 0.5 half of the MP value తీసుకోవాలి. ఓకే, అర్థమవుతుందా? అదే ఓన్లీ ద డిఫరెన్స్. సో హియర్ ఇన్ ప్రాపర్డ్ క్యాంటిలివర్ ఫస్ట్ హింజ్ విల్ ఫార్మ్ ఎట్ సపోర్ట్, రైట్, MP, అండ్ డ్యూ టు ప్రాపర్డ్ క్యాంటిలివర్ దిస్ సపోర్ట్ ఈజ్ ఆల్సో ప్రొడ్యూసింగ్ సమ్ ప్లాస్టిక్ మూమెంట్. ఓకే, ఇక్కడ కూడా హింజ్ ఫామ్ అవుతుంది. అది ఎంత, హాఫ్ ఆఫ్ ద హింజ్ ఫామ్ అవుతుంది, విచ్ ఇస్ 0.5 of MP is equal to WL/4. ఓకే, WL/4 is the maximum moment. Okay, cantilever beam is subjected to point load with some distance, right? So WU ultimate load is equal to 6 into MP/L. This is the equilibrium method. అదే వర్చువల్ వర్క్ మెథడ్ ద్వారా చూడండి, WE is equal to WI, which we have to do. WU of L/2 into theta. So what is theta? ikkada theta. So this is theta, right? WU into L/2, ఈ డిస్టెన్స్ ఎంత, L/2. L/2 of theta is equal to MP of, ఇక్కడ ఒక theta ఉంది కదా, theta plus 2 theta. ఓకే, సో MP into theta plus 2 theta. So this is the applied moment and this is the resisting moment. ఓకే, సో దిస్ ఈక్వల్ చేస్తే ఏమొస్తుంది, 6 MP/L. సో ఇక్కడ కూడా చూసారా, 6 MP/L. So this is how for proper cantilever beam the collapse load is going to be calculated. ఇవన్నీ స్టాండర్డ్ ఫార్ములాస్ అమ్మా, ప్లీజ్ ట్రై టు రిమెంబర్. ఓకే, 6 MP/L is for the proper cantilever beam. Fixed beam with eccentrical load is 2 MP into L/AB. మీరు గుర్తు లేకపోతే మీరు క్యాలిక్యులేట్ చేసుకునే విధం మీకు తెలిసి ఉండాలి. ఓకే, సో చూడండి ఎన్ని మన ఎగ్జాంపుల్స్ చేసామో. ఫర్ సింప్లీ బీమ్ వి డన్, ఫర్ ఫిక్స్డ్ బీమ్ విత్ UDL load, for a fixed beam with a point load, for fixed beam with eccentrical load, for a proper cantilever beam also we have done, right? ఈ 5 examples మీరు ఒక్కసారి రివైజ్ చేసుకున్నారు అంటే, సో క్యాలిక్యులేటింగ్ కొలాప్స్ లోడ్ ఈజ్ వెరీ వెరీ ఈజీ. సో ఎందుకు ఆ లోడ్ ఇంపార్టెంట్? దాట్ కొలాప్స్ లోడ్ ఈజ్ ద వన్ విచ్ మేక్స్ మెంబర్ టు మేక్ ఫెయిల్ అట్ ఇట్స్ అల్టిమేట్ కెపాసిటీ. ఓకే, ఆ లోడే ఆ మెంబర్ని ఫెయిల్ చేస్తుంది. ఓకే, ఇప్పుడు మీరు స్ట్రక్చర్ మీద ఏదైతే లోడ్స్ మీరు డిజైన్ చేస్తున్నారో దట్ లోడ్ ఈజ్ నాట్ ఫర్ ఫెయిల్యూర్, దట్ లోడ్ ఈజ్ ఓన్లీ విచ్ ఈజ్ మేకింగ్ దట్ మెంబర్ అండర్ ఈక్విలిబ్రియం స్టేట్. ఓకే, సో ద కొలాప్స్ లోడ్ ఈజ్ నథింగ్ బట్ ద లోడ్ వేర్ ద మెంబర్ ఈజ్ సబ్జెక్టెడ్ టు ఫెయిల్. ఓకే, ఆ కొలాప్స్ లోడ్ క్యాలిక్యులేట్ చేయడం కోసమే వీఆర్ యూజింగ్ దిస్ ప్లాస్టిక్ అనాలిసిస్. వై? బికాస్ ఇన్ ప్లాస్టిక్ అనాలిసిస్ వీ క్యాన్ ఏబుల్ టు క్యాలిక్యులేట్ ద అల్టిమేట్ లోడ్ at where your member will subjected to failure. Okay, yeah. So now ఇంకొక ఎగ్జాంపుల్ ఉంది, propped cantilever with UDL load. So let's see propped cantilever with UDL load, right? So hinge will form at support, right? And this is the bend moment diagram and this is the shear force diagram. Avuna? So this triangle is the shear force diagram and this is the bend moment diagram, isn't it? So this is the maximum positive bending moment and this is that collapse, right? So this moment is at the collapse load. So let's see how it gonna calculate with big statements. So because where we have to go with few things to calculate. So here WU is equal to 11.656 MPa by L square. So this is what the maximum collapse load with the help of equilibrium condition. ఓకే, ఇలా కొన్నిటికి స్టాండర్డ్ ఫార్ములాస్ ఉంటాయి, కొన్ని మనం క్యాలిక్యులేట్ చేసుకోవాలి. ఎలా క్యాలిక్యులేట్ చేసుకోవాలి? యూ హ్యావ్ టు నో ద maximum bending moment of this member, then only you can able to calculate the collapse load with the help of an equilibrium method. Okay, so ఇక్కడ ఒక చిన్న ఎగ్జాంపుల్ ప్రాబ్లం కూడా ఉందమ్మా. సో we can go through and we can able to calculate what is the plastic moment capacity of this member. ఇప్పుడు చూడండి, a proper cantilever beam which is subjected to two concentrated loads at some distance 1.5 meter from the support, 1.5 meter from the free end, I mean from the propped end. Okay, so total length is 7.5 meter. So can you tell me what is degree of indeterminacy? Here the degree of indeterminacy is 3 is for fixed support, 2 is for pinned support, and the degree of indeterminacy is 1. Number of hinges, ఇక్కడ ఎన్ని hinges form అవుతాయమ్మా? As a fixed support, one hinge will be here, right? As it is a pinned support, one hinge will be here, and as it will bend like this, sorry, ikkada kaadu, ikkada. At this concentrated load, one hinge will form, and at this concentrated load, one hinge will form. At this fixed support, one hinge will form. So total hinges are 3. Ikkada kaadamma hinge. Okay, 3 hinges. One plastic hinge here, here, and here. Because I already told you, plastic hinges will form at supports. Plastic hinges will form at point loads. Akkada kuda plastic hinges form అవుతాయి. Okay, and number of independent mechanisms ఎన్ని? R is equal to n minus n. N is the number of hinges and capital N is the number of indeterminacy, and number of independent mechanisms are 2. అంటే దీంట్లో 2 మెకానిజమ్స్ ఫామ్ అయ్యే ఛాన్స్ ఉంది. 2 మెకానిజమ్స్ అంటే ఏంటి? 2 విధాలుగా ఈ బీమ్ బ్రేక్ అయ్యే ఛాన్స్ ఉందన్నమాట. ఏంటి ఆ 2 వేస్? మీకు ఫిగర్స్లో చూపిస్తాను. దిస్ ఈస్ ద ఫస్ట్ వే. ఓకే, this is the first way where we have to calculate the plastic moment. Okay, second way enti? This is the second way. చూసారా, 2 డిఫరెన్స్ ఉన్నాయా? This is what 2. Number of independent mechanisms are 2. ఇక్కడ మనకు 2 వచ్చింది కదా. What is this 2? 2 means this beam having a plastic moment in 2 forms. This is first form. అంటే హింజ్ ముందు ఫస్ట్ పాయింట్ లోడ్ దగ్గర యాక్ట్ అయితే ప్లాస్టిక్ మూమెంట్ ఎంత? వి క్యాలిక్యులేటెడ్ 45.83. అదే హింజ్ సెకండ్ పాయింట్ లోడ్ దగ్గర యాక్ట్ అయినప్పుడు ఎంత? విచ్ ప్లాస్టిక్ మూమెంట్ ఈజ్ 87.5 కిలోన్యూటన్. మరి రెండిట్లో మ్యాక్సిమం వాల్యూ ఏది? 87.5 కిలోన్యూటన్. సో బై దట్ డిజైన్ ప్లాస్టిక్ మూమెంట్ highest of the above, which is 87.5. So by that I have to design this beam, which is this beam, to plastic moment of 87.5 kilonewton ki design cheyali. Enduku? ee moment daggara your beam will fail. Okay, so whatever you are designing your beam should be designed for 87.5 kilonewton into meter, okay, to take care of its ప్లాస్టిక్ బెండింగ్ స్ట్రెస్సెస్. ఓకే, అందుకని మనం క్యాలిక్యులేట్ చేస్తాం. ఇక్కడ 2 మెకానిజమ్స్ రావడమే మనకి ఇక్కడ 2 నెంబర్. ఓకే, సో ఒక్కొక్క మెకానిజం చూద్దాం ఒకసారి. దిస్ ద ఫస్ట్ మెకానిజం. సో హియర్ విచ్ మెథడ్ ఐఎమ్ యూజింగ్? హియర్ ఐఎమ్ యూజింగ్ వర్చువల్ మెథడ్. ఎందుకు? సి, ఫర్ ఎ కామన్ ఫార్ములాస్ లైక్ సింప్లీ సపోర్టెడ్ బీమ్ టు పాయింట్ లోడ్, యూడిఎల్ లోడ్, we know the bending moment formulas. But when there are multiple loads like this, beam subjected to 2 point loads, point load with UDL load, point loads 3-4 point loads, అలా ఉన్నప్పుడు maximum bending moment formulas ఉండనప్పుడు ఏం చేయాలి? Without knowing the maximum bending moment formula, we can't make use of the equilibrium method. Okay, then we have to go with the virtual work method. Virtual work method ద్వారా మనం moments ని calculate చేయొచ్చు అనమాట. Okay, so let's see how to calculate the moment with the help of virtual work method. Why? Because your proper cantilever is subjected to 2 concentrated loads. There is no direct bending moment formula for this. అందుకని. ఓకే, సో చూడండి, ఫస్ట్ మెకానిజంలో హింజ్ డెఫినెట్గా సపోర్ట్ దగ్గర ఫామ్ అవుతుంది. ఇంకొక హింజ్ ఎక్కడ ఫామ్ అయింది? ఈ కాన్సన్ట్రేట్ లోడ్ దగ్గర ఫామ్ అయింది. రైట్, ఇవి ఎలా క్యాలిక్యులేట్ చేస్తాను చూడండి. 50 into ఇక్కడ యాంగిల్ ఎంత ఫామ్ అయింది టీటా, దిస్ ద యాంగిల్ 50 into 1.5 into theta. చూడండి 50 into 1.5 into theta ప్లస్ ఓకే మళ్ళీ 75 into ఇట్ సైడ్ కదా 75 into 1.5 into 1.5 by 6 into theta. Okay, so this angle is how much? Theta 1. How to calculate theta 1? Theta 1 ఇక్కడ ఆల్రెడీ క్యాలిక్యులేట్ చేశారు చూడండి. In the mechanism 1, what is the value of theta 1? 1.5 into theta is equal to 6 theta 1, where theta 1 is equal to 1.5 by 6 of theta. ఈ యాంగిల్ టీటా అయితే ఈ యాంగిల్ ఎంత అవుతుంది? ఈ యాంగిల్ 1.5 by 6 times of theta అవుతుంది. ఓకే, ఇక్కడ మనం ఏం చేసాం 50 into 1.5 times of theta plus 75 into 1.5 times of theta 1. What is theta 1 value? 1.5 by 6 into theta, which is equal to resisting plastic moment. ఎంత? mp of theta plus theta 1 plus theta. అవునా? సారీ ఇది కాదమ్మా, టీటా ప్లస్ టీటా 1. ఇవే ఎందుకు ఈ మూడే కన్సిడర్ చేస్తున్నా, ఇది నేను ఎందుకు కన్సిడర్ చేయట్లేదు? బికాజ్ ఇట్స్ ద ఫస్ట్ మెకానిజం. యువర్ ప్లాస్టిక్ హింజెస్ ఆర్ ఫార్మ్డ్ ఓన్లీ విత్ ఇన్ ద లిమిట్. ఇక్కడ వరకే ఫామ్ అయ్యాయి. ఓకే, ఇక్కడ వరకే ఫామ్ అయ్యాయి కాబట్టి టీటా ప్లస్ టీటా 1. ఎంపీ ఆఫ్ టీటా ప్లస్ టీటా 1. వాట్ ఈస్ టీటా 1? 1.5 by 6 into theta. Then what is the value of MP? MP is 45.83 kilonewton into meter due to plastic hinge which is formed due to load of 50 kilonewton. Okay, second mechanism చూద్దాం. This is the second mechanism. Second mechanism లో plastic hinge ఎక్కడ ఫామ్ అయింది? ఇక్కడ ఫామ్ అయింది. Okay, so this is theta and this is theta 1 and this is theta plus theta 1. ఇది theta 1, ఇది theta, right? Okay, so now 6 theta is equal to 1.5 times of theta 1. ఎందుకు 6? ఇది 4, 5, 6. So this distance is 6 meters. Okay, this distance is 1.5 meter, right? So 6 meters ki theta అయితే 1.5 meters ki ఈ angle ఎంత? 6 theta is equal to 1.5 times of theta 1, where theta is equal to 1.5 by 6 times of theta 1. Okay, so now this is the plastic mechanism. So by mechanism 2 మనం క్యాలిక్యులేట్ చేద్దాం. 50 into 1.5 into theta. అవునా? చూడండి 50 into 1.5 into theta. 1.5 into theta. What is the value of theta? 1.5 by 6 into theta 1 plus 75 into 1.5 into theta 1. 75 into 1.5 into theta 1 is equal to, right? Plastic moment and the plastic moment of theta. What is value of theta? 1.5 by 6 into theta 1 plus theta 1. అవునా? చూడండి theta plus theta 1. ఓకే, ఇది వాల్యూ theta plus theta 1. ఓకే, calculate MP 87.5 kilonewton into meter. So this is the maximum. See, out of these two, when your proper cantilever is subjected to 2 point loads, the possibility of forming plastic moment is due to 75 kilonewton force వల్ల ఫామ్ అవుతుంది. అంటే ఇది ఒకటే కాదు, ఈ ప్లాస్టిక్ హింజ్ క్యాలిక్యులేషన్ చేయడం వల్ల మనకి మ్యాక్సిమం మూమెంట్ క్యారీ అవుతుంది. ఓకే, సో బై దట్ వీ హ్యావ్ టు డిజైన్ దిస్ పర్టికులర్ బీమ్ ఫర్ ఎ మూమెంట్ ఆఫ్ 87.5 kilonewton, which I am going to consider it as a collapse load. ఓకే, సో ఇలాగ మనం క్యాలిక్యులేట్ చేస్తాం. చూడండి, వర్చువల్ వర్క్ మెథడ్ కూడా చాలా ఈజీ అమ్మ. ఓకే, అదేం పెద్ద కష్టం కాదు క్యాలిక్యులేట్ చేయడం. రైట్, అందరికి అర్థమైందా? క్లియర్? శ్రీనివాస్, రజనీష్, ఎవ్రీవన్? ఓకే, that's it, Amma. So this is the best example where I can share with you to calculate the plastic moments based on the plastic hinge theory, so which is the plastic analysis. Okay, so here finally I want to conclude. Here we learned about what do you mean a plastic analysis, what is the difference between elastic analysis and plastic analysis, what do you mean plastic section modulus, what do you mean plastic moment, what do you mean shape factor, how to calculate the collapse load, how to calculate the plastic moment for the few examples like determinate beams and indeterminate beams. Okay, so this is what we explained okay, in the today's class. So any doubts you can ask me. That's it. Okay, so thank you guys. I think I have done my best in explaining you the plastic analysis. So this is very, very important for all competitive exams related to civil engineering. Okay, so please go through all these concepts again, because this video will be with you, I mean in my Facebook live. So you can go through many times, and if you have any doubts, please comment at the video itself. I will try to answer your questions, guys. Okay, right? So tomorrow what we are going to do is, tomorrow as usual we will have our schedule with 10:30 to 12:30 in the morning session. So where I will start with plastic analysis theoretically. You know, presentation ichanu kada. So tomorrow I will try to cover few more topics on plastic analysis theoretically on paper, and then we will go through the beam concepts. Why? Because we have to design all beams under plastic analysis only. Enduku plastic analysis? Why? Because beams are subjected to lateral forces. So beams subjected to bend. So beam should have a maximum resistance towards bending. So maximum resistance towards bending, it should be calculated based on the plastic analysis only. Okay, in that way, plastic analysis concept is very much important in designing the beams. Okay, so there we will come up with the plastic section modulus and elastic section modulus sectional properties manaku akkada vastayi. Okay, and the importance of the shape factor also will be seen in the designing of the beams. Okay, so the difference you need to understand, what is the difference between the elastic moment and the plastic moment. Okay, always plastic moment will be more than the elastic moment. It's based on the geometry of the different sections available, right? Praveen oka doubt adigadu, is uniformly distributed load acting, how will calculate, sir? Chusaru kada, oka example chusam kada. See, when the uniformly distributed load is acting, there is no formation of plastic hinge. Plastic hinge uniformly distribution load lo act avadu. Meeku konni points cheppani, ee points maatrame gurtu pettukondi. These are the points. Chudandi, where the plastic hinges will form. First, the plastic hinge will form at maximum moment. The point of maximum moment, plastic hinge will form at the connection involving change in geometry, under the concentrated load, at the point of zero shear in span, loaded by uniformly distributed load. Uniformly distributed load lo ekkadaithe zero shear force untundo, ekkada, if it is at center, so you can take plastic hinge at center. Here one example I can show you. Chudandi, fixed beam subjected to UDL load. Ekkada form ayindi plastic hinge? Center lo form ayindi, right? In a fixed beam which is subjected to UDL load, Praveen, Vintanava, fixed beam when it is subjected to UDL load, why the plastic hinge formed at center? Why? Because at this point the shear force is, what is the shear force? 0. Shear force is 0 by considering this beam as simply supported beam. అవునా? మరి షియర్ ఫోర్స్ 0 అయినప్పుడు పాయింట్ ఆఫ్ ప్లాస్టిక్ హింజ్ ఎక్కడ ఫామ్ అయింది? సెంటర్లోనే ఫామ్ అయింది. ఇదే ఎగ్జాంపుల్. సో అట్ దిస్ కండిషన్స్ ఆల్సో యూ క్యాన్ గో విత్ ద అండ్ క్యాలిక్యులేట్ ద వాట్ ఈస్ దిస్ కొలాప్స్ లోడ్, రైట్? యూడిఎల్ లోడ్ కూడా తీసుకోవచ్చు. యూడిఎల్ లోడ్ దగ్గర ఇక్కడే ఉంటుంది. So this is theta and 2 theta. MP of theta plus 2 theta plus theta, which is equal to 2 times of, why 2 times? Because of 2 plastic hinges at supports, W into L by 2 of UDL load. What is UDL load? Which is this, right? So UDL load అనేది మనకి it should be acted in a form of a point load కాబట్టి L by 2 into theta by 2. Okay, so that distance I need to take. ఎందుకు మీకు అందరికి తెలిసిందే కదా, ఇది ఇది యూడిఎల్ లోడ్. వాట్ ఈస్ ద సెంటర్ పాయింట్ ఆఫ్ దిస్ లోడ్? ఇప్పుడు ఇది W అనుకోండి, ఓకే, ఇది లెంత్ L అనుకోండి, What is this centroidal distance? W into L into L by 2. మర్చిపోయారా? అంతే. This is what the UDL load acts at the center of this span. W into L is the load acting at a distance of L by 2. ఓకే, సో ఇది కూడా అంతే. 2 into U into L by 2 is the load. L by 2 into theta అనేది ఏంటి? Distance. This is the L by 2 into theta by 2. Okay, which is the half of the portion. Okay, which is equal to MP of theta plus 2 theta plus T. Okay, UDL load కదే example. Right. Thank you, Praveen. I hope you understood. Right. What about others? Anusha Reddy, clear ఉందమ్మా? అర్థమైందా ప్లాస్టిక్ అనాలిసిస్? హౌ టు క్యాలిక్యులేట్ ద ప్లాస్టిక్ hinges అర్థమైందా? వేర్ టు లొకేట్ ద ప్లాస్టిక్ హింజ్, హౌ టు క్యాలిక్యులేట్ ద కొలాప్స్ లోడ్, ఇది చాలా ఇంపార్టెంట్. ఓకే, సో ఇవి మీకు అర్థమైతే, సో ఐ థింక్ ప్లాస్టిక్ అనాలిసిస్ ఈజ్ bit easy to where you can answer questions which you come across in your competitive exams. Rest of others, అందరూ చెప్పాలి, అందరూ నాకు ఆన్సర్ చేయొచ్చు ప్లీజ్. మీకు అర్థమైందా? ఎక్కడైనా డౌట్స్ ఉంటే చెప్పండి. నేను ఐ విల్ ట్రై టు ఎక్స్ప్లెయిన్ యూ వేర్ ఎవర్ ఇఫ్ డౌట్స్ యూ హ్యావ్. కన్నాదాసన్, అందరూ చెప్పాలమ్మా, బికాజ్ సాటిస్ఫాక్షన్, సాటిస్ఫైయింగ్ ఎవ్రీ స్టూడెంట్ ఈజ్ వెరీ ఇంపార్టెంట్. ఓకే, ఐ హోప్ మీకు ఏమైనా కొద్దిగా అర్థం కాకపోతే ఎనీవే పీపీటీ ఈ ప్రజెంటేషన్ ఉంది కాబట్టి యూ క్యాన్ జస్ట్ గో త్రూ అగైన్ అండ్ లెట్స్ సీ హౌ యూ గోనా అండర్స్టాండ్ దిస్ కాన్సెప్ట్. ఓకే, అండ్ ఎందుకంటే అందరూ ఒకేలాగా దీన్ని అర్థం చేసుకుంటారని అనుకోను, బికాస్ సచ్ అన్ ఈజీ అట్ ద సేమ్ టైమ్ ఇట్ ఈస్ బిట్ టఫ్ టు అండర్స్టాండ్. ఓకే, అంత ఈజీ కాదు అర్థం చేసుకోవడం ప్లాస్టిక్ అనాలిసిస్. సో బై దట్ యూ షుడ్ బి వెరీ స్ట్రాంగ్ ఇన్ బేసిక్స్ ఫ్రమ్ స్ట్రెంత్ ఆఫ్ మెటీరియల్స్ ఇట్ సెల్ఫ్. So how the plastic analysis, what is the pure bending equation there, what is the maximum bending moment formulas, okay, so what do you mean hinge, what do you mean fixed support, ఇవన్నీ మీకు అర్థమైతేనే ఈ అనాలిసిస్ అనేది మీకు బాగా అర్థమవుతుంది. వెరీ గుడ్, అనుషాకి అర్థమైంది, సరోజిని ధరంకి అర్థమైంది, వెరీ గుడ్. ఓకే, వర్చువల్ మెథడ్ ఈస్ బిట్ కన్ఫ్యూజ్డా? ఏం లేదు అనుష, వర్చువల్ మెథడ్ కూడా చాలా ఈజీ, బికాస్ యూ హ్యావ్ టు లెర్న్ ద వర్చువల్ మెథడ్. అదర్వైజ్ సే ఫర్ ఎగ్జాంపుల్ బీమ్ సబ్జెక్టెడ్ టు యూడిఎల్ లోడ్, పాయింట్ లోడ్, ఇలా అన్ని లోడ్స్ ఉన్నాయనుకోండి, అప్పుడు యూ కాంట్ మేక్ యూజ్ ఆఫ్ ఈక్విలిబ్రియం మెథడ్, బికాస్ దెర్ ఈస్ నో స్ట్రైట్ అవే ఫార్ములా ఫర్ ఏ బీమ్ సబ్జెక్టెడ్ టు మల్టిపుల్ లోడ్స్. ఓకే, సో మల్టిపుల్ లోడ్స్ ఉన్నప్పుడు మీకు డైరెక్ట్గా మ్యాక్సిమం బెండింగ్ మూమెంట్ ఫార్ములా ఉండదు. సో దెన్ యూ హ్యావ్ టు గో త్రూ ద డిఫరెంట్ మెకానిజమ్స్ టు క్యాలిక్యులేట్ ద మ్యాక్సిమం ప్లాస్టిక్ మూమెంట్. ఓకే, అప్పుడు కంపల్సరీ మీరు ఇది నేర్చుకోవాల్సిందే. రైట్, ఇక్కడ చూడండి ఎందుకు పెద్ద కన్ఫ్యూజన్ ఏముంది ఇక్కడ. సో ఈ ముందు ఎన్ని మెకానిజమ్స్ ఫామ్ అయ్యే ఛాన్సెస్ ఉన్నాయి అనేది ఈ ప్రాబ్లంలో జస్ట్ గో త్రూ. ఓకే, చూడండి చిన్న ఈ ఎగ్జాంపుల్ ప్రాబ్లం అందుకే చూపించాను నేను. ఈ ఎగ్జాంపుల్ ప్రాబ్లంలో 2 మెకానిజమ్స్ ఫామ్ అవుతాయి. ఒకటి డ్యూ టు దిస్ కాన్సన్ట్రేటెడ్ లోడ్, సెకండ్ వన్ ఈజ్ డ్యూ టు దిస్ కాన్సన్ట్రేటెడ్. ఈ కాన్సన్ట్రేటెడ్ లోడ్ ఒకసారి, ఈ కాన్సన్ట్రేటెడ్ లోడ్ వల్ల ఒకసారి ఫామ్ అవుతాయి. రైట్, సో ఆ మెకానిజమ్సే నేను ఇక్కడ చూపించాను. సో చాలా సింపుల్, లోడ్ ఇంటూ డిస్టెన్స్ 50 ఇంటూ 1.5 ఇంటూ టీటా ప్లస్ 75 ఇంటూ దిస్ డిస్టెన్స్ 1.5 ఇంటూ టీటా. టీటా వాల్యూని ఇక్కడ డిఫైన్ చేశాను. టీటా 1 ఏంటి? 1.5/6 ఇంటూ టీటా. ఓకే, ఇక్కడ టీటా 1.5 డిస్టెన్స్కి ఇది టీటా అయితే ఈ టోటల్ డిస్టెన్స్కి ఇక్కడ టీటా ఎంత? ఓకే, సో అది మనం ఇక్కడ డిఫైన్ చేస్తున్నాం అంతే. రైట్, సో ఎందుకంటే ఫస్ట్ మెకానిజంలో ఏం చేయాలి తెలుసా? యూ హ్యావ్ టు కన్సిడర్ ఓన్లీ దిస్ లోడ్ అండ్ ద రెస్ట్ ఆఫ్ పోర్షన్ షుడ్ బి ఎంటీ. 4, 5, 6. 4.5 plus 1.5, 6. 6 into theta 1 is equal to 1.5 into theta. అదే నేను ఇక్కడ రాసింది. 1.5 into theta is equal to 6 into theta 1. అప్పుడు theta 1 ఎంత అవుతుంది? 1.5/6 into theta అవుతుంది. అందుకే 7.5 into 1.5 into theta 1 ని మనం ఇలా రాసాం, విచ్ ఈజ్ ఈక్వల్ టు ద రెసిస్టింగ్ ఏంటి? ఎంపీ ఆఫ్ theta plus theta 1. అలా ఎంపీ క్యాలిక్యులేట్ చేస్తాం. ఓకే, సెకండ్ మెథడ్ కూడా అంతే. సెకండ్ మెకానిజం కూడా యాజ్ యూజువల్ 50 ఇంటూ డిస్టెన్స్, 75 ఇంటూ డిస్టెన్స్. ఓకే, ఇప్పుడు ఏం చేయాలి? ఈ పాయింట్ లోడ్ని కన్సిడర్ చేసుకోండి, ఈ డిస్టెన్స్ 6 మీటర్స్ తీసుకోండి. ఓకే, సో అప్పుడు యూ హ్యావ్ టు క్యాలిక్యులేట్ టీటా వాల్యూ. 6 ఇంటూ టీటా ఈజ్ ఈక్వల్ టు 1.5 ఇంటూ టీటా. అండ్ వాట్ ద వాల్యూ ఆఫ్ టీటా? 1.5/6 ఇంటూ టీటా 1. ఓకే, ఇక్కడ ఇది 6 మీటర్స్ డిస్టెన్స్. ఓకే, ఇక్కడ ఇది 6 meters distance. Okay, then 50 into 1.5 into theta plus 75 into 1.5 into theta 1, which is equal to mp of theta plus theta plus theta 1. theta value ఆల్రెడీ ఇక్కడ ఉంది, దెన్ mp క్యాలిక్యులేట్ చేసాం. చూడండి, చాలా ఈజీ, ఏం పెద్ద టఫ్ ఏం కాదు. ఫర్ హింజ్ సపోర్ట్ వీ కన్సిడర్ హాఫ్ mp. దెన్ వాట్ అబౌట్ రోలర్ సపోర్ట్? ఓకే, సో హియర్ వాట్ యు ఆస్క్డ్, ఇక్కడ ఒక చిన్న ఎగ్జాంపుల్ జరిగింది కదా. యా, హియర్ ఇన్ ద ప్రాపర్డ్ క్యాంటిలివర్, at this support there is a possibility of hinge due to this prop. Sorry, not this. ఇక్కడ కదా. యా, సో దిస్ ప్రాపర్డ్ క్యాంటిలివర్ బీమ్లో ఇక్కడ హింజ్ ఫామ్ అయింది, ఇక్కడ హింజ్ ఫామ్ అయింది, ఇక్కడ హింజ్ ఫామ్ అవ్వలేదమ్మా, రైట్? సో దిస్ ఈస్ ద పాయింట్ వేర్ ఇట్ ఈస్ మేకింగ్ సింప్లీ సపోర్ట్. అందువల్ల అక్కడ ఒక ఎంపీ తీసుకున్నాము. 0.5 ఎంపీ ఎందుకు తీసుకున్నాము అంటే, ప్రాపర్డ్ క్యాంటిలివర్లో దీని నుంచి కూడా మనకి దెర్ విల్ బి ప్లాస్టిక్ హింజెస్ విల్ ఫామ్. ఇక్కడ ఒక హింజ్ కూడా ఫామ్ అయింది, రైట్? సో ఈ ఫిక్స్డ్ సపోర్ట్ నుంచి ఒక హింజ్ తీసుకుంటాము. ఇలా ఎప్పుడైతే ప్రాపర్డ్ ఉంటుందో దెన్ వీ హ్యావ్ టు గో విత్ 0.5 ఆఫ్ ఎంపీ ఆల్సో ఫర్ క్యాలిక్యులేటింగ్ ద వాట్ ఈస్ దట్ అల్టిమేట్ లోడ్, రైట్? ప్రాపర్డ్ క్యాంటిలివర్కి ఈ హింజ్కి కూడా మనకి రిలేషన్ ఉంటుంది. సో వెన్ ఇట్ ఈస్ ఎ ప్రాప్, యూ ఆర్ సపోజ్ టు టేక్ 0.5 ఆఫ్ యువర్ ఎంపీ తీసుకోవాలి ఎప్పుడు ప్రాపర్డ్లో. ఓకే, ఎప్పుడు ఈక్విలిబ్రియం కండిషన్ చేసేటప్పుడు. అర్థమవుతుందా? క్లియర్? ప్రాప్ ఉన్నప్పుడు, ఎందుకంటే చూడండి, ఫిక్స్డ్కి మనం ఎంపీ తీసుకుంటున్నప్పుడు పిన్నిడికి, నేను ఇక్కడే చెప్పాను, పిన్నిడికి ఎంత తీసుకోవాలి? 0.5 ఎంపీ తీసుకోవాలి. అందుకే 0.5 ఎంపీని ఈక్విలిబ్రియం కండిషన్లో పెట్టాను. ఓకే, మీరు ఈ ఎగ్జాంపుల్లో రిలేట్ చేస్తున్నారేమో. ఈ ఎగ్జాంపుల్లో నేను అసలు ఈక్విలిబ్రియం కండిషనే చేయలేదు కదా. ఇన్ దిస్ ఎగ్జాంపుల్ ఐ డెంట్ డూ ఎనీ ఈక్విలిబ్రియం కండిషన్. ఇఫ్ యూ డూ ఈక్విలిబ్రియం కండిషన్, యూ హ్యావ్ టు గో విత్ 0.5 ఎంపీ at prop support and MP at fixed support. Clear, Anusha? Anusha, clear అయిందా? ప్రాప్డ్ క్యాంటిలివర్లో హింజ్ ఉంటే అక్కడ 0.5 ఎంపీ తీసుకోవాలి. అంటే హాఫ్ ఆఫ్ ద ప్లాస్టిక్ హింజ్ తీసుకోవాలి, ప్లాస్టిక్ మూమెంట్ యాక్ట్ అవుతున్నట్టు. ఓకే, ఫుల్ హింజ్ ఉందనుకోండి, ఫిక్స్డ్ ఉందనుకోండి, అక్కడ ఒరిజినల్గా హింజ్ ఫామ్ అవుతుంది కాబట్టి సో అక్కడ మీరు ఫుల్ ఎంపీ తీసుకోవచ్చు. ఓకే, ఇలా ఫిక్స్డ్ ఉంటే ఫుల్ ఎంపీ, ప్రాప్డ్ ఆర్ ఎనీ పిన్నెడ్ సపోర్ట్ ఉంటే 0.5 ఎంపీ తీసుకోవచ్చు. ఓకే, బట్ మేక్ షూర్, మళ్ళీ ఇంకో డౌట్ రావచ్చు మీకు, సార్ సింప్లీ సపోర్ట్లో 2 ప్రాప్స్ ఉన్నాయి కదా, మరి 2 ప్రాప్స్ ఉన్నప్పుడు మీరు 1 ఎంపీ ఎందుకు తీసుకున్నారు? అవును, మీరు ఆలోచించండి. ఇక్కడ కూడా 2 ప్రాప్స్ ఉన్నాయి, ఇక్కడ 0.5, ఇక్కడ 0.5, రెండు కలిపి అంతా 1 ఎంపీఏ. అందుకే నేను 1 ఎంపీ తీసుకున్నాను. ఇక్కడ మీరు ఫస్ట్ రావచ్చు చూడండి, ఫస్ట్ ప్రాబ్లంలో ఇదిగో సింప్లీ సపోర్ట్లో నేను డైరెక్ట్గా సింగిల్ హింజ్ ఐ క్యాన్ టేక్ ఎట్ మ్యాక్సిమం బెండింగ్ మూమెంట్, ఆర్ ఎల్స్ నేను ఇందాక మీకు చెప్పిన కాన్సెప్ట్ ప్రకారము ఒక హింజ్ ఉన్నప్పుడు 0.5 ఎంపీ తీసుకోవచ్చు. ఇక్కడ 0.5 ఎంపీ, ఇక్కడ 0.5 ఎంపీ, రెండు 0.5 ఎంపీస్ కలిపి సింగిల్ ఎంపీ. అలా కూడా మీరు యూ క్యాన్ కన్సిడర్ ఇట్. ఓకే, రైట్? యా, సో ఐ థింక్ అనుష అండర్స్టూడ్. సాయి కృష్ణ కట్ట, ఎస్, వెరీ గుడ్. సో ఫైన్ everyone, so I think I've done my best to make it understand clearly. So any doubts, so please try to put your comments in, so by that I can able to clear your doubts later on also, right? So let's wait for tomorrow's class. Anyone? So can I take a leave today, guys? Please respond. Okay, so what is the time now? It's 3:53. Very good. So as per my schedule, I thought to make it for 2 to 4. So it is almost 4 now. So I think we had a good explanation even on the presentation, right? Anything else, guys? Anything you want to question? No? No questions? Praveen, Anusha, you both understood. Sai Krishna also understood. Rishi, yeah, he is also understood. Rishi Vardhan Reddy. Sarojini is understood. Praneeth is watching. Kanna, Praneeth, are you fine, guys? Okay then, yeah. So then see you tomorrow. Okay, anything you can just put your question over there, right? Thank you so much.